So we have two resistors, a 555 timer. What are we missing now? Let's just double check. We're in hardware here. Hardware. Sorry, wiki. We have a 10 microfarad capacitor and a 10 nanofarad capacitor to go. Let's add those in. So let's put capacitor. Oh, we forgot to add the footprint, hey? So you can see the footprint in our 1 kilo ohm is here, but in our 10 kilo ohm, we haven't added anything yet. So we're going to get an error if we try to create a PCB from this. So let's add the footprint. Same one, since we made sure to pick the same package size. Lots of different types of capacitors. There's aluminum electrolytic capacitors. Those are polarized. So one side is positive, one is negative. And if you try and use it backwards by accident, you might blow it up. Ceramic capacitors are pretty common, super cheap and very small. Tantalum capacitors are also well liked, but they're toxic. So if you blow them up, you're not gonna do so well. We'll stick with ceramic because they're pretty cheap. One thing you need to be careful with when picking your capacitor. So again, we like active parts. We like parts that are in stock. Unlike a resistor, where the resistance is probably the most dominant characteristic of a resistor, capacitor, the capacitance is important, but also the voltage rating. So we're looking for a 10 microfarad, right? Yeah. 10 microfarads. Really impressed with how fast DigiKey is. It's lightning speed. Alright, 10 microfarads, cool. So you need to be careful here. Ceramic capacitors have a problem called they call it voltage bias sometimes, or voltage derating. So if I look up ceramic capacitor, okay, capacitor derating. This is a very well-known sort of property of capacitors, especially ceramic ones. Basically, that their capacitance is not constant according to the voltage across them. So if I have a 10 microfarad capacitor with 5 volts across it, it's actually going to exhibit a different capacitance than if 10 volts is across it. That capacitance changes almost by 10% in this case. These are pretty good capacitors. So you need to be very careful about what voltage your capacitor is rated for and what voltage it's actually going to operate at. So you can see here, like, these ones change dramatically with the voltage across them. So like a common general rule of thumb you can do is, if your capacitor is supposed to operate at some voltage, then a reasonable voltage rating to pick is double that voltage. So if we're going to run at 5 volts, we can pick a 10 volt rated capacitor. This is not the most scientific way to do this, but it's easy and quick if you need a fast solution. If you're very concerned with the exact capacitance you need to use, temperature conditions, if the voltage is changing across your capacitor, then I'd highly recommend to start looking into the data sheet of your capacitor and how it's derated specifically by the manufacturer. There's lots of resources online. Here, temperature and voltage variation, rating and derating so they call them MLCCs, multi-layer ceramic capacitors. And there's a ton of stuff here called DC bias. Look at another one. Read the data sheet. Most important thing. They're not always the same. And like COG versus Y5 versus X5 and X7, different dielectrics will have different temperature ratings. And then also different changes in capacitance. So you can see like X7R and X5R have different ratings than other capacitors. Those are basically they tell you what temperature your capacitor can handle. In our case, we're not using any capacitors for power systems, so they're not going to heat up too much, which is nice. So we can just pick the cheapest one. So we specified 10 volts, we specified 10 microfarads. Anything else we care about? These are different classes of capacitors. There's Y class, there's X class. They all have different sort of applications. Let's try and go for the same 0603 size. Cool, in stock, apply. So let's go to quantity 1. And just double check that the cheapest one is actually 50 cents. No, it's not, 31 cents. That's pretty pricey actually. But it looks like it's the cheapest one for the specs we gave. It might be cheaper at a different package size, maybe 0402 or 0805, but let's stick with 0603 for the sake of simplicity. So click on this one. That's okay, there's 40,000. Copy. Let's just double check that this capacitor shows us the dimensions, because a lot of them don't. Alright, perfect. Altium, part search. You know the drill by now. Nice and fast. We'll get all those parameters set up with only a few clicks of your mouse. Great. Import. Get rid of this. And just double check, all the parameters are here, super nice, 10 microfarads, a 603 X5R dielectric, which specifies the max temperature it can run at. 10 volt rating. So one of the things we usually like to do for capacitors is to show the rating, so that when it's in your schematic, you can see both the capacitance and the voltage rating. So you can tell the user like what the capacitor is rated at and what they should expect the performance to be, especially if it's a multi-layer ceramic capacitor. Let's use our same trick as before and steal that capacitor symbol. This is good. Copy. Oh, sorry. Oh, that's right. Let's paste it here. And put 10 volts right under. Make sure we have a reference designator set up. C question mark. And then for the comment, 10 microfarads. Both looks good. Don't have our footprint yet, so let's add that in. Footprints. Tools, IPC compliant. Next, chip, yeah. Okay, now we'll switch to chip capacitor. So what are the sizes here? This is double check for 603, good. Length 1.6 plus or minus 0.15. So what is that? Some quick math. 1.75. Body width range. 0.8 plus or minus 0.15. 0.65. 0.95. Forgive me if my math is wrong here. Terrible at arithmetic. Body width range, or sorry, bandwidth range. So that's these little bands here, E, so 0.2 to 0.55. And our maximum height, T, 0.95. Yeah, looks good. So they're quite a bit taller than resistors. Non-polar, remember that was for an electrolytic capacitor, this is a ceramic capacitor. And this is kind of gross, so let's generate this step model preview. There you go, it's your capacitor. Next. Step file, footprints, looks good. Let's add a quick silkscreen overlay bounding box. Up here. Cool, change the name quickly, C0603. Awesome. It's slightly different than the R1. You can see the pads slightly different. So you can't use the same one for both, but they're pretty similar. Let's add that to our symbol. CO603. Awesome. Cool, so we're getting there. We have one more capacitor and an LED to do, and then we're done all the parts. We can start on the schematic. So what's our capacitor? 10 nanofarads. So again, it can change this capacitance filter. 10 nanofards. So that would be 0.01. Come on. So 10,000 picofarads, is that a nanofarad? I think so. And we'll keep all the same other ratings. Awesome. We're still at unit quantity 1, and we still have this showing increasing prices. So our cheapest one is here. 450. This is if you were using this for a real, if you were like manufacturing this board and actually putting it together, I'd be wary of 450 with also fluctuating lead times, because you might run out of parts. Maybe you should go for something like one of these. This is 4,000. Let's do this one. This is more. This is less worrying. The copy, no pictures, not as pretty. That's okay. Looks good. What do I do now? Part search. Good. Hope you guessed that. Always part search. Cool. 10 nanofarads. 1. Import. Get rid of this. This is long and gross. Doesn't mean anything. Again, let's take the symbol, copy it, paste it in here. Cool. And then designator C. And then 10 nanofarads. Parameters, we want to show that voltage again. Where's our voltage? There you go. Show it. Popped up. Put it right under. Looks good. Let's add our footprint, and then we can go to our LED. Cool. Let's just see what we got so far and push it up. Status. Add a commit and added 10 kilo resistor and 10 nanofarad resistor, 10 nanofarad, 10 nanofarad capacitor. Cool. Okay. One LED. So you can just look up LED. Active. It's nice to pick LEDs with the lowest forward voltage possible, just because they require less voltage to turn on. Some are really annoying and take like 2 volts or more, but it probably won't hurt us too much if we have a 1.9, 2 volt kind of deal. It's really hard if you have an LED that's trying to be powered off 3.3, because then you have to be careful. Like say 2.8, or that blue LED needed 2.8 volts to turn on, which is getting close to your 3.3, and the other one needed 3.6. So this would definitely not be able to be turned on with 3.3 volt rail. So we have 5 volts available, so we should be okay. You can also specify your wavelength if you really like to. I don't know anyone who does. Sometimes you can specify the brightness. Do you have that? Or you can specify the millicandela, how luminous your LED is, as well as like the viewing angle, only from the top or from as wide as possible. We like surface mount ones. And we'll just go for a classic green, I think. So only 3 available. Oh, we specified this by accident. Let's get rid of this. Okay, 5,000 is more like it. 21. Okay. Let's grab this guy. It's a red one. I wanted green. Is there a green one here? More expensive, eh? Yeah. Okay, let's grab this green guy. Light on. Pretty standard. It's in a 603, and it might be slightly different. So let's double check what the recommended pad size is for this LED. Hopefully they'll specify in the datasheet. Okay, so you can just create these pads in Altium. Copy. Schematic library. Classic part search. We're your last one, finally. I like to make sure to pick ones that show the unit price because we know it's quantity 1. What's annoying though is Altium doesn't have these in Canadian. You can specify the different currencies, but not Canadian for some reason. Annoying. Cool. Hide. LED. General designator. LEDs are diode, so use D. And for the comment, we can use the manufacturer part number like the IC. Some people like to put maybe the forward voltage, or some people put the color. I think the color is a better indicator of what this part is. So green, and then let's take that symbol from the diode, from the Altium libraries. So someone spent a lot of time creating this, which is nice. Schematic loop. Cool. And then our footprints. Let's see if we can use one of these footprints already, actually. So they liked 0.8, 2.3, 0.8 by 0.8. Okay, what do we have here? Control M to measure. Something like this. 2.54. 1. Okay, it's a little big. Let's create a new one. So this time we're not going to use an IPC compliant footprint wizard because I don't think actually, no, I don't think they have LED models here. So we can just create our own pads. So we won't have a nice step file for this one, like a nice 3D model like these, but that's okay. So we'll do tools, new blank footprint for once. And just label this. I'm going to call it LED 0603. Cool, so we'll learn how to place pads now. Place pad. And it starts as a circle, but if you hit tab, you can change it. And we don't want it to be multi-layer. These colors, what they mean, this sort of greeny teal kind of color, that means through a hole. So this is a hole straight through your whole board. This silver color will be exposed copper. So it's like a nice big pad for your soldering iron to touch and for you to flow solder through. So it's really helpful. And then this purple is solder mass expansion. So if I switch to top layer, it's all red now, which means it's just a pad on the top of the board and there's no holes straight through, which is what we want in our case. But we don't want it to be a circle. So let's go rectangular, and we know it's 0.8 mm by 0.8 mm square. Awesome. So let me just move it. I like to start with the first one in the center, and then we need to move the other one. Does it specify how far exactly? So there's some math to be done here. 2.3 minus 0.8 is 1.5. So the centers are 1.5 millimeters apart. Is that right? 1.5. Yeah, I think so. So this one needs to move 1.5 millimeters over. One trick I like is to take the second pad and actually place it right over top the first one. I'll just right click to exit this command. So they're right on top of each other, but what you can do is click it, press M like mango, then move selection by X or Y, and I'm going to want to move it by X, 1.5 mm to the right. To the left would be negative, so I can negative 1.5, but we want it to the right, it's 1.5 mm, and it'll move it by 1.5 mm to the right, nice and easy. Control M to measure, double check. Oh, I missed there. Shift C will clear. Control M, 1.5 mm. Pads are just under, my grid isn't exactly the right size. You can change that here. Differences. Where is it? Grids. You can change these grids here to be smaller or bigger. I'll just keep it as it is now because it's pretty standard. So this is about 0.8, 1.5 mm apart, looks good. One thing you notice that's different is this mechanical layer. So this is the actual 3D file that Altium provided to generate capacitor. We don't have that in our case. But what we should do is still create this mechanical outline. It's actually hiding right now. So this green outline around. And I might just steal this one, so I'm going to click all of them while holding Shift. And one more here. Control C. And when you copy something like this in the PCB editor, or the footprints editor, once you hit Control C, there's going to be another cursor. And so what that cursor is doing is asking you where you want to copy it from. So if I click this top left corner, when I paste it, it's going to paste as if I was holding that top left corner. Control V, because I'm holding that top left corner. I can just put this right here. So it's a nice mechanical outline. It'll really help at the end when we see all our mechanical outlines. And we'll do the same thing with the overlay, so I'm going to show that now. Also going to steal it. Oh, I don't want this. Yeah, there you go. And this is actually the green one, the yellow. Yeah, Control C. I'm going to pick this bottom right corner now, and we'll see that when I paste it, it'll be from that bottom right corner, as if I was holding it. Awesome. So this looks good. Let's put it here. Awesome. I have a nice little bill of materials, our own parts library for our project, and we're ready to create the schematic now.